All right, you ready to have your mind bent a little bit? Because we are diving headfirst into quantum physics. And look, this isn't just some abstract, dusty old theory. This is, well, it's pretty much the instruction manual for the entire universe. And the craziest part? We all have to play by its rules. You know, the physicist Brian Cox, he puts it perfectly. We have this tendency to think there's our normal world, right? And then there's this other bizarre quantum world over there with its own separate, wacky set of rules. But that's just not true. The rules that tell a tiny little electron what to do, they're the exact same rules that are holding together the chair you're sitting on right this second. There's only one playbook for all of reality. So that leads to the big question, doesn't it? I mean, if the rules are the same for everything, why does the quantum world seem so completely bizarre, so counterintuitive to us? Why doesn't a baseball act like an electron? That is the mystery we're going to try and unpack together. Okay, so think of it like this. Our everyday, predictable world, the one we see and touch, it's kind of like the surface of the ocean. You know, it seems pretty calm, it follows certain rules, but underneath that surface, down in the quantum depths, there's this swirling, almost chaotic world of pure possibility. Our reality, it's just what emerges when you average out all of that microscopic weirdness. So you might be asking, why should I care? Well, here's why. This isn't just some philosophical debate anymore. This is real. We are actually building technology right now that harnesses all this weirdness. Take quantum computers. They aren't trying to ignore these strange rules. They're built specifically to take full advantage of them. Honestly, understanding this stuff is no longer optional. It's becoming the key to our future. All right, let's get right to the heart of all this weirdness. It really all boils down to one single core concept. And we can understand it with a really simple idea. Let's call it the quantum coin. Okay, just look at the difference here. A normal, classical coin, it's always either heads or tails. Simple. Even when it's flipping through the air, it has a definite state. We just don't know what it is yet. But a quantum coin, think of an electron, is totally different. It can literally be in a state of both heads and tails at the exact same time. This isn't about what we know or don't know. The particle itself is in this blurry mix of all possibilities at once. And that right there is called superposition. And you see, this completely changes how we have to think about probability. Like when a weather report says there's a 50% chance of rain, that's just because we have incomplete information, right? We don't know everything about the weather system. But in the quantum world, wow, the uncertainty isn't about what we know. The particle itself is fundamentally uncertain. That probability is baked right into the fabric of reality. So that's it. That's superposition. It's the ability of a particle to be in multiple states at the very same time, right up until the instant you measure it. And hey, according to physicists like Brian Cox, if you can really wrap your head around this one deeply strange idea, you've basically unlocked the biggest secret of quantum mechanics. Okay, so how in the world do we know any of this is actually real? I mean, it sounds like science fiction. Well, it turns out there's one incredibly famous experiment that just perfectly encapsulates all of this weirdness in one go. You've probably heard of it. It's called the double-slit experiment. And the setup is it's beautiful in its simplicity. So you have a gun, and it fires single electrons, okay? Just one at a time. These electrons, they travel towards a barrier that has two little vertical slits cut into it. And then, on the other side, there's a detector screen that just records where each electron hits. Now, think about this for a second. If electrons are just tiny little bullets, what would you expect to see on that screen? I mean, common sense tells us we should just get two simple bands, right? One lined up behind each slit. That makes perfect sense. Yeah, but that is not what we see. Not even close. Instead, we get this bizarre striped pattern. This is what's called an interference pattern. It's the kind of thing you'd expect to see if waves were passing through the slits and interfering with each other, not solid little particles. But here's where it gets truly wild. This pattern shows up even when you fire the electrons one by one. Just think about that for a second. The only way that is possible is if each individual electron is going through both slits at the same time, and then interfering with itself. It's in a superposition of paths. That is a very, very strange picture of reality. Okay, so we've established that a single particle can be in multiple places at once. Wild stuff. But what happens when you take two of these quantum particles and link them together? Well, that's when we run into something that even the great Albert Einstein found deeply unsettling. He called it spooky. We call it quantum entanglement. So entanglement is this phenomenon where two particles become linked, so linked that their fates are just perfectly intertwined. Whatever you do to one particle instantly, and I mean instantly, affects the other one. And it doesn't matter how much distance is between them. This is what Einstein famously called spooky action at a distance. Here's a great way to think about it. Imagine you entangle two particles. You keep one right here on Earth, and you send the other one all the way out to Pluto. The moment, the very instant you measure the particle on Earth and find that its spin is up, you know with 100% certainty that the particle on Pluto is now down. That connection, it's instantaneous. It happened faster than the speed of light. So I know, superposition, entanglement, it all sounds incredibly abstract, right? Almost philosophical. But it is this very weirdness that we're talking about that gives quantum computers their almost unbelievable power. Think about it. A regular computer bit is simple. It's either a 0 or a 1. That's it. But a quantum bit, or a qubit as we call it, thanks to superposition, it can be a 0 and a 1 at the very same time. So what does that mean? Well, with just 2 qubits, you can represent 4 different combinations all at once: 0, 0, 0, 1, 1, 0, and 1, 1. And this is where the magic really happens. The power doesn't just add up, it grows exponentially. Every single qubit you add to the system doubles its power. So 3 qubits can hold 8 values at once, 4 qubits hold 16, and it just keeps exploding from there. This exponential growth leads to a number that is just truly mind-blowing. Get this, with just 500 entangled qubits, you can represent more states at the same time than there are atoms in the entire known universe. Just let that sink in for a moment. We're talking about more information than all the atoms in existence, all held inside a single tiny machine. So what does that kind of power actually mean in the real world? Well, it means that a problem that would take the most powerful supercomputer we have today billions of years to solve, and I mean literally longer than the age of the universe, a quantum computer could potentially crack in a matter of minutes. That is the incredible, world-changing power we are just now beginning to unlock. So let's just end with a final thought to bring this all back home. We know, from that double-slit experiment, that a single particle explores every single possible path at once to get to its destination. Many physicists believe this isn't just a mathematical trick, it's a literal truth about how reality works. So if that's true for the fundamental building blocks of our universe, what does that say about the one single path you think you're on right now?